What is the difference in the two time periods? 1. That is, and we know that if the data are stationary, the covariance between yt and yt minus 1 is the same as the covariance between yt minus 1 and yt minus 2, is the same as yt minus 7 and yt minus 8, because what matters is how far apart they are rather than what the t index is. So therefore this is nothing but covariance between yt and yt minus 1, because covariance of one period apart, which we know, okay, and of course this will not be alpha because covariance alpha is a constant, so covariance between alpha and yt minus 2 will be 0, right? I forgot to write that off, okay, is equal to phi, and you know phi sigma square e upon 1 minus phi square, sure, which will be equal to phi square sigma square e into 1 minus phi square, right? This is gamma 2, autocovariance at order 2 is phi square sigma square upon 1 minus phi square. So what will be autocorrelation at lag 2? Rho 2 will be autocovariance divided by the variance. Where did alpha go? Constant. So what will be the covariance of a constant with yt minus 2? 0, no? Yeah. Okay. Right. So what will be rho 2? Rho 2 will be autocovariance upon variance. Phi square sigma square upon minus phi square upon sigma square upon minus phi square, which will be phi square. Right? Okay. Now from this you should tell me what will be the covariance at lag 3? yt minus 3. This will be phi cube sigma square upon 1 minus phi square will be the autocovariance at lag 3. Autocorrelation at lag 3 will be phi cube. Autocorrelation at lag 4 will be 5 raised to 4. Autocorrelation at lag 5 will be 5 raised to 5, and so on. Right? Sure? So we know once. So first, for a stationary AR1 process, okay, for a stationary AR1 process, gamma 1 gamma 2 gamma raised to j, so on, right? Okay. So if you are told that sigma square e is always equal to 1, suppose I tell you that the error term is normally distributed, is a standard norm, sigma square is equal to 1, and if I tell you the value of phi, will you be able to find gamma 1, gamma 2, gamma 3, gamma 4, gamma 5, gamma 6 and so on? Right? Do you think that the autocorrelate covariance will subsequently keep on becoming smaller and smaller and smaller? Yes. Right? Because higher powers of phi are involved, no? Phi square will be less than phi, phi cube will be less than phi square, absolutely phi is less than 1. It means that the importance of yt for yt plus 2 is less than the importance of yt for yt plus 1. The more you go into the future, the less relevant does the knowledge of current yt become. The less relevant does the knowledge of current yt become. The future, the impact of yt slowly wears off. That's what we saw in a stationary process anyway. Right? So that's really captured here. Now if I tell you that if you have a process where yt is equal to 2 plus 0.5 yt minus 1 plus et, and et is a standard normal process, what would be gamma 1? So if you substitute here, what gamma 1 be? Sigma square is defined to be 1. What will gamma 1 be? Do it on small. You have a cell phone with a calculator? 2 by 2. What will be gamma 2? Gamma 2 will be 1 by 3?
Yes.
Sure? Calculate gamma 2. So 0.5 square will be in the numerator, 3 by 4 will be the denominator, right? So 1 upon 4 upon 3 by 4 is 1 by 3, correct. What will be gamma 3? What will be gamma 3? One by 6? Do it all of you have small, you don't have a cell phone? Please take your cell phone out. Such a simple sum to do, no? But this is a very important idea, so please understand this carefully. Solve करें
1 by 6.
1 by 6. And so on. So now you see that if I give you the value of j, you can always find out gamma j.
Yeah.
So if you kept gamma j, for example, so if you put j here and if you put gamma j here, if j is equal to 0, that's going to be sigma square e upon 1 minus pi square, because this is really gamma is j, no? So if j is equal to 0, gamma 0 is going to be like this. So that's going to be 1 in our sigma square e upon 1 minus pi square, whatever that value is. That might start with somewhere, and then you will have a function which slowly goes off like this. This is called the autocovariance function. This is called the autocovariance function. Right? It's called the autocovariance function. ACF. ACF of an AR1 process. It's called an ACF of an AR1 process. Okay? ACF of an AR1 process. Right? On the other hand, if I try to find the autocorrelations, then the autocorrelation at lag j is phi raised to j. So at lag 0, it's phi raised to 0, it's 1. White is perfectly correlated to itself. At lag 1, it's phi raised 5. At lag 2, it's phi square. Lag 3 is phi cube. Lag 4 is 4. So if you plot that, you have a plot of the autocorrelation function. So important point is, for a stationary AR1 process, the autocorrelation function ACF, okay, the autocorrelation function ACF or the autocovariance function both will die off, will become slowly approach the x-axis, become smaller and smaller and smaller. If phi is a negative quantity, it will keep on fluctuating like this and keep on dying off, because phi cube will be negative, phi raised to 4 will be positive, and so on. It will fluctuate like this and die off. If phi is positive, it monotonically decline. Right? So that's something important that we have learned today, the idea of the autocorrelation function of a stationary AR1 process. Whereas for a non-stationary process, all this doesn't work because there is no autocorrelation. Right? Because all those are phi's and those are not defined really. Sure? So you can't use that for non-stationary process. This whole thing that I am going to teach you only works for stationary processes. The point is, people discovered this methodology before they learned that there were processes which were stationary and non-stationary. They were applying it for everybody. And then suddenly in the 1980s, these two guys came and said, look here, there are non-stationary processes and for which all this theory doesn't work. This is called the Box-Jenkins methodology. It's a very popular forecasting tool which came out in the 60s. And for 20 years, we were happily forecasting. Right, all sorts of time series using Box-Jenkins, and then in the 80s we learned that many series this can't be applied, right? And it was found actually by a man called Nelson and Charles Plauser that a large number of macroeconomic time series were actually non-stationary like this. So it created a whole revolution in the world of forecasting and statistical modeling, which is still with us. Then people began to look at different techniques and how do you deal with it? Macroeconomic time series are non-stationary. How do you deal with them? If you can't use the TF, chi-square Z, what do you do? And therefore a whole set of new statistical techniques developed in the 80s and the 90s and the 2000s and 2010s, and they also continue to be developed in the 20s and the 30s, etc., to be able to do better and better statistical modeling. How much more time do we have?
Half and half.
Half n. Right. So is this clear? This is autocovariance. Autocorrelation will be 5. 5 raised to j, 5 raised to 5 cube, 5 raised to 4, 5 raised to 5. Right? Autocovariance as well as autocorrelation. Because even the 5 raised to j will keep on giving falling. No? Sure, folks? Are we through this? Do you have any difficulties at all? No? Now I can make this process a little bit more complicated. For example, I can write this process as